Good morning. Today's seminar is by Juan Suarez, a colleague of our group and also a friend. Juan Carlos, it's a native from La Laguna, in fact, and he obtained his degree in astrophysics here at our Department of Astrophysics at the University of La Laguna back in '99. So he just was awarded with one of these ISC's international grants for doing a PhD in foreign countries. And he moved on '99 to Observatoire de Paris-Meudon in France. And he started the PhD thesis with a very reputed group in France led by Goupil. So he finishes the PhD in 2002, and he moved since then to the Instituto de Astrofísica de Andalucia, where he has been working since then. So he managed to obtain some postdocs as anyone else. In fact, now he has one of these excellence program postdoc fellowship, which, by the way, I think it finishes this year. So I guess we'll have a new Ramon y Cajal very soon. So this is my wish, and I think Juan Carlos is in a very good track for it. His field of work has been since the beginning asteroseismology. In fact, asteroseismology of intermediate mass stars. In particular, he is a lover of the Delta Scuti and Gamma Dor stars. In these stars, he has been interested in all the rotational aspects, dynamical aspects, using the asteroseismology tools, in fact, studying interaction between pulsation and rotation in the interior of the stars, and also the effects on the surface physics, turbulence and convection. So, in these years, he has been involved in different projects. If I well remember, he is the PI of one of the virtual observatory tools, programs. He developed a tool for asteroseismology in the virtual observatory in Spain. He is the leader of one of the working groups in the space mission, CoRoT, working mainly in Delta Scutis. And for the last 2 years, he is one of the Spanish representatives in the board of the PLATO mission. This will be the focus of his talk. Let us know what's PLATO, what it represents in the context of the ESA Cosmic Vision program, and also the opportunities for science. So the production of Juan Carlos along these years is remarkable. More than 60 or 70 papers, referee papers. But here I would like to stress that in the last 8 years, he has been able to be the supervisor of 3 very successful theses. So I think this is one aspect that tells a lot about Juan Carlos. So, Juan Carlos, that's your turn.
Thank you very much, Pere. First of all, thank you for coming. Good morning. I would like to thank Pere, Clara, and the group of stellar physics here in ISA to invite me to work with them and to give me this opportunity for giving a talk today. Well, today we'll speak about PLATO. PLATO was not only a philosopher, but is also this means also planetary transits and oscillations. This is the natural evolution of other previous space missions like MOST, CoRoT, and the Kepler mission. And now this mission is one of the 3 currently alive in the ESA Cosmic Vision 2021, I think. And normally ESA will take a decision at the end of this year, around October. and only 2 of these 3 missions will be retained. Well, the main characteristics of PLATO are the following. It is an M-class mission of ESA. It's a medium class. Currently, it is in definition phase. As I said before, in competition with other 2. These other 2 are Solar Orbiter and Euclid. It seems that Solar Orbiter is out of discussion, so in principle the direct competition is with Euclid. And as I said before, we will know the decision of ESA at the end of this year. The main objectives of the missions are to detect and characterize planetary systems. I would like to highlight this word characterize, because the other 2 missions currently in flight, CoRoT and Kepler, are more focused in the detection by itself of planetary system, planets and so on, and to make senses of these planets, to know more about statistics and so on. But the main idea of PLATO is not only to detect planets and planetary systems, but to be able to characterize them. That is, to know at least some of the essential parameters like masses, radii and ages of the planetary systems, and with high accuracy, not only for the planets but also for the hosting stars. The instrument is a multi-telescope, which is needed because it is intended to have a very wide field of view. Very wide field of view means that means a lot. I will show you a slide at the end of the talk with what represents this very wide field of view. It is something like 20,000 degrees in the sky at the end of the mission, which is very huge. The techniques are not new. PLATO will detect planets using the transits method, and it will use astroseismology for the characterization of the hosting stars and the planets. It will take advantage of ground-based observations, new instrumentation which is being now developed for ground-based observations for high-resolution spectroscopy, which is needed to measure radial velocities, which are necessary to confirm the transits. And by that time, normally, if everything goes well, GAIA will be flying, so we'll have the data from GAIA, which is very, very interesting for us. And well, finally, PLATO will observe in the main case around 300,000 stars, bright stars, lower than 13, with magnitudes lower than 13, which is new compared with the other missions, as I will explain after CoRoT and Kepler. Well, so I will speak a little bit about the context of the mission, the main science goals, SICT, the design concept, which is currently in mind, the expected performances of the mission, and the Spanish contribution and the future steps. Well, just to put you in context, so far the planets which have been detected are large planets, like Jupiter-like planets. In the last decades, this is what we have detected. Now, we are now detecting, thanks to CoRoT and Kepler missions, planets with sizes and masses around like Neptune-like planets, and super Earth, which is around twice the mass of the Earth, or 4 times the radius of the Earth. But the idea is that PLATO goes further in order to to find Earths. Well, in fact, Kepler is maybe able to find some Earth-like planet at the end of its life. Now I think Kepler is flying by 2 years approximately, but maybe in other 2 years smaller planets will be detected. But in fact this is the main case of PLATO, and by the characteristics of PLATO is more likely to finding such planets better than any other mission. Well, this is what we call the discovery space. In that plot, you can see a relation of planets detected with their masses, their mass of the planet detected in Earth masses versus the distance to the host star in astronomical units. In blue, you can see planets detected using the transits. In green, planets detected using radial velocities, and in red are far planets detected using the microlensing technique. Lines are the detection threshold needed using the current ground-based instrumentation. And here, the domain that PLATO is intended to populate is this one. That is, planets, small planets around, well, Earth-like planets with a distance of 1 astronomical unit. That is another solar system. Here you can see the distribution of detected planets as a function of their masses. As you can see, the main peak is around 10 Earth masses, which is Jupiter-like planets, and well, it is. We think that this peak is caused by observational bias due to the period and the capacity of observing such planets so far. And but the theoretical studies, like one of Mordassi and collaborators from 2009, predict that small planets should be populated in that region more than it is now. PLATO will be the only mission that can check this. We don't know if this is the case in the future, but the only way to check is with a mission like PLATO. Well, the main science goals of the mission. Well, the main science goal is to understand how planetary systems form and evolve. This is why we want to characterize them. It is essential to understand, to have the main characteristics of the hosting stars and their planets, including ages, because it's one of the way to compare one system with another, and in that way to compare and to know how those systems evolve. To do that, we count with the heritage, as I said before, of other missions like CoRoT and Kepler. The only problem of those missions is that they are focused on faint stars. In the case of CoRoT is for stars with magnitudes larger than 11, and the case of Kepler is for stars with magnitudes larger than 14. This is a problem when you want to first confirm the transits that you have detected with your space satellite, and then when you want to characterize the stars, you need to properly characterize the global parameters of stars, like effective temperature, for instance, radius, masses, and so on, luminosities, in order to properly or take advantage of this nice technique which is called astroseismology. But astroseismology needs of very accurate measurements in order to provide very accurate results in terms of ages, radii, and masses. So to do that, we need a mission able to have ultra-high precision with a high duty cycle, long duration, and at the same time observe bright stars. This is what PLATO will do. In fact, here, this is the target scheme. This is the main goals. The main goal of the mission is to observe around 20,000 bright stars, lower than 11, focused on cool dwarfs and subgiants with these spectral types, in order to find around them exoplanetary transits and to be able to make good seismic analysis and to have an ultra-high precision in radial velocity follow-up required, as I said before, to correctly characterize the stars. And to do that, we need at least a noise lower than this quantity, 2.7 10 to the -5 in 1 hour, and this for 3 years. So it really is a real challenge for the mission. It is currently in discussion the operational mode of the mission, of the observing mode, I mean. But depending on this observation mode, for instance, focus in 2 fields during 3 years, or just maybe 2 years, and then you change in some months some of the targets. This is currently under discussion. But what is important is that at least the scientific requirement is to observe around 1,000 very bright stars. I mean, lower than 8, or depending on the mode, the 3,000 very bright for 5 months. It's depending on that. But in addition to this, PLATO will observe around 250,000 cool dwarfs lower than 13, magnitude 13, for which the PLATO will be able to detect exoplanetary transits and make the follow-up. But not only that, because with this huge field of view and this operational mode, this mission will be able to observe plenty of other different stars. Giants, red giants, Delta Scuti, AF stars, or plenty of stars. So this can be a very, very nice repository of stars, most of them very well studied and very well determined their masses, radii, and ages, thanks to astroseismology. So this can be very, very interesting for many other fields in astrophysics, using population of stars and models and so on. Well, just to give you an idea, what PLATO will need to do is, this is a comparison of an exoplanetary transit already observed by CoRoT. This is a light curve with a little dip. This dip corresponds to a planet transit. Is the plot in the up there. This corresponds to CoRoT 7b. As you can see, the planetary transit is 0.035% of the 0 point of the light curve. So this is very tiny. But if we want to observe in a simulation we have made, if we want to observe, this is for a super Earth, CoRoT 7b. I think it's around 2.5 radii of Earth radii, twice the mass of the Earth. But if we want an Earth around one Sun at the distance of one astronomical units. This is much lower than the CoRoT 7b. Is around 0.01 percent. The deep. So it's really tiny, and to be able to detect that and confirm that this is a deep due to a planetary transit, we need a really stable system with a very low noise. Here I show you a table which compares the radial velocities required on Earth to confirm or detect planetary transit for different planet sizes and different planet distance to the host star. And PLATO is mostly interested in the lower part, so around here. That is super Earth and Earth are at about 1 astronomical unit of the star. So we need something like 0.5, well, lower than 1 meter per second, and for 1 Earth is 10 centimeters per second. To do that, we will count with some ground-based facilities like HARPS North here in Canary Islands, some of them here in Canary Islands also, and other spectrograph like Espresso and CARMENES. This last one, CARMENES, will be able to make a full dedicated program for follow-up for PLATO, because their main scientific case will end when PLATO will be launched around 2018, if I remember well. CARMENES, in fact, is more focused to infrared, but this is can be very interesting for low-mass stars that PLATO will be able also to observe. In addition, at the beginning of this talk, I told you that we will use astroseismology to characterize the planetary system, including the host star. Well, in fact, it's the host star that will be characterized by astroseismology. But when you are able to characterize properly with high accuracy and precision the masses and radii of stars, you can also characterize with the same precision, or even more, the planets' sizes and masses. And here I show you an example of a typical oscillation spectrum from star for a solar-like star, a star like the Sun. Astroseismology is able, using some characteristics of this spectrum, to determine mean densities and be able to probe the core of such stars, giving you an idea. Giving you the age of the star with very accurate precision. And on the right panel, I show you an example of this. A recent example of this is one of the planets discovered by Kepler. Is HATP7, and there I show you. Well, it's not very well. I think it's the radius determined by using astroseismology by models. All these black points are models, and the red line is the precision that you have using the standard techniques, using spectroscopy and so on, radial velocities and so on. And when you use astroseismology, you are able to reduce the uncertainty to this, which is very low, around, well, you can, it's not very well seen, but there, whoops, well, okay. This is between 1.9 and 2.2 solar radius if I remember well. So it's a very, very tiny precision. In fact, the expected uncertainty using astroseismology for masses and ages is around 2 and in percentage, sorry, and 10% for the age, which is very, very accurate compared with standard stellar physics. Another interesting point is that astroseismology is not only interesting to characterize the global parameters of stars like masses and radii, but also is the only technique today able to probe the stellar interior. So thanks to missions like CoRoT, Kepler, and now PLATO, it is possible to have very accurate data which serve us to probe this stellar interior. This is very interesting for me in particular. I'm interested in this mission. My domain of expertise, as Perez said before, is the interaction, rotation, pulsation. And so roughly what I seek is to be able to find the internal rotation profile of stars, in particular AF main sequence stars, but also solar-like and any other. And the problem today is that even with CoRoT and Kepler, we are not able to resolve the rotational splitting caused by rotation in the oscillation spectrum. This is an example. On the right, you can see is a typical oscillation mode splitted by rotation, perfectly resolved. But, well, when you superpose all the rest of the modes due to lifetime or due to precision of the measurements and etc., we are not able today to resolve such splittings for stars like AF main sequence stars nor solar-like stars. It is possible for other, but not for these stars, which are generally, for example, AF stars are generally fast rotators, and it is essential to know what happens inside the star in order to be able to build correct models. Why correct models? An example of that is these are two evolutionary tracks. One of them do not take rotation into account, and which is the black one, and the others, the blue one, red, etc., take rotation into account. These are very different evolutionary track, and this only taking into account some basic hypotheses on rotation. But what we know is that, for instance, the interior of the star can be rotated differently from the surface, and this is important for. This can be connected also with what happened with convection and diffusion of elements, and this may change a lot the evolutionary models. And of course, this is important for other branches in astrophysics that use stellar models. Well, the design concept has had to answer a challenge, which is to have at the same time a wide field of view and a large collecting area, because we need that the photon noise is very low, as I said before, and we need to observe as much as stars as possible, and also a very stable environment, in order that any noise source is unless lower than 1/3 the photon noise. So this concept has evolved from the first one from Astrium, proposed by Astrium, of 12 reflective telescopes and 14 CCDs per focal plane, to the current one, which is similar to the one to the right, proposed by Thales Alenia, with refractive telescopes. Well, in fact, the current one is just this one, with 34 telescopes with 4 CCDs per focal plane of 4K by 4K pixels. This design currently responds to the mass and power budgets required for the mission required by ESA to be launched. The mission satellite will be in L2, as everything. Everything is at L2, it seems. It will observe 2 fields with an observing mode of 3 + 2 years. Well, as I said before, this is something that is being discussed. We don't know yet exactly if it will be 3 years + 2 or with 2 years plus some observing modes of 5 months and so on. We don't know yet, but more or less at least 3-4 years will be the nominal time of the mission. Well, concerning the expected performances, here I show you a comparison between what is expected to found in at the end of the mission of Kepler mission, and what is expected to found at the end of the PLATO mission. Well, these diagrams relate the mass of planets in different regions, from the smaller one to on the bottom to the more massive on top, and then with the distance to the hosting star in the semi-major axis. The semi-major axis normalized to the axis necessary to be inhabitable zone. So the main gain of PLATO is to be able to go to this right bottom part of the panel, that is to find very small planets, Earth-like planets, at a distance similar to the solar system. That is 1 astronomical unit. And this gain is due to the brightness. Really, the important point of this mission is to focus on bright stars, which give the possibility of confirming the transits and to be able to characterize the stars, which is the key point for to characterize these planetary systems. So, as you can see, well, in blue is the performances for PLATO, and in green is for Kepler. So, really, PLATO will be even more performant at any point of the diagram, but even more at the key point, which is Earth-like planets. Another interesting point is that the impact of the masses and radii measurements. Here I show you an example of this is a radii in Earth radii as a function of the masses for the planets. The different lines are the different type of rocky planets, considering things like the origin of these rocky planets, iron spheres or ice spheres or whatever, different theories that which are today dealing with in this area. And the red point is CoRoT 7b, it's a super Earth, and different triangles are the Earth and Venus. Well, normally the typical error bar in those diagrams for the radii and masses are this. So let's say that the uncertainty to choose between one theory and another is quite large, and for any part of the diagram. But with PLATO, we will be able to have those error bars. This accuracy is huge compared with what we have now. And it is possible not only to characterize those systems, but also to, for the first time, to be able to speak about planet diversity. And this diversity and this constraint on the radius and masses is very important when to study the planet atmospheres, and it is very interesting when you want to to select some targets for further missions that are focused in studying planet atmospheres, for instance. Well, now I will speak about the Spanish contribution and a little bit about the organization of the mission currently. The Spanish contribution is twice. On one side is the industrial contribution, and on the other side is science. For the industrial contribution, today the commitment is to develop two parts of the instrument. One part is the focal plane assemblies, whose responsible is Miguel Mas Hes, who is working in INTA CAP in Madrid. He's actually the coordinator of the mission in Spain. And the other part is the main electronic unit, that is the electronics that will make the image acquisition of each telescope. And the responsible is me in Granada. Well, I have to say that now the mission is, as I said before, in definition phase, and definition phase is currently being made by industry. In fact, it's Thales Alinea Spain, which is doing this work. And if the mission is retained by October of this year, is when these two part of the instrument will be split by INTA and EA in Granada. Miguel Mas and myself, we are both in a PLATO mission consortium. That is, we are both the Spanish representative, as Perez said, of the mission, and we are in charge to make the communication between the main, let's say, the main board and the different and the Spanish contribution, and the industrial Spanish contribution. Yeah, I say that. Concerning the organization, though, this is really a mess, like any other ESA project, with different contribution of countries and depending on their industrial contribution or scientific contribution and so on. There are two parts here that can be seen, and Spain is represented. These two parts are just what I have mentioned about the Spanish contribution. Here it is. Here and here. But in these boxes, there are other boxes similar to this. I'm not going to explain that because it's really a mess. But just to say that not only there is a industrial participation, but also participation in work packages. In those work packages, the Spanish contribution is the following. There is a work package that whose coordinator is myself, which is called End Product Guarantee. This package is intended to verify that there is no inconsistency between what we are finding and we expect to find in terms of final product, that is masses, radii, etc. And light curves preparation, which is led by Andrés Moya in the CAPS-SIC. This preparation concerns the let's say cleaning the light curves from planetary transit to be sure that we are properly doing astroseismology only to oscillation modes and no to planetary transits. Determination of limb darkening. This is the leader is Antonio Claret, also in my institute. Detection of planets around binary stars. The leader here is Hans Deck, who is here in the audience. The HI diagram and chemical abundance study by Carlos Allende, also here in ESA. But in addition of these, there are other work packages in which people in Spanish group are also involved, or at least interested, which is ground-based and follow-up activities, for which we will use the Observatory of Sierra Nevada, Carrer Alto, and ESA facilities, and also spectrographs like CARMENES, HARPS, so on, etc. Plus science, and this I have to say that now we are, I think it's in the next slide, even if the PLATO consortium, international consortium, has been created last year to answer of the announcement of opportunity of the ESA, the Spanish consortium, of course, if the mission is retained by October, should be defined by the end of this year, November, December, etc. And the idea of Miguel Mas and myself is to make a 1 or 2 days science meeting for the people in Spain interested in doing science for the mission. Well, I will send this announcement in the following months after knowing if the mission is retained. But the idea is that today, even if work packages or and the structure of work packages more or less closed because we needed to deliver this structure to ESA, there are plenty of things which are open, even to the possibility of leading other packages. For not only for the main case of the mission, which is doing exoplanetary system characterization, seismology, and so on, but any other things, but plenty of other things. There will be, like in the CoRoT and Kepler missions, an additional science, in which if you are interested, you can send a letter of intent and just to lead another work package to do whatever you want, if in the possibility of the mission, of course, for the using the PLATO data. So this is very interesting, and I encourage you to go to this 2 days meeting in order to, if you are interested, and just to see if we can do more science than the main case here in Spain. Well, I just finish here. Thank you. I thank you for coming, but just before ending, just to show you the field of view of PLATO compared with the other two is really, really huge compared with CoRoT, for instance, which is here, very tiny, and Kepler, which is very big compared with CoRoT, but nothing compared with PLATO, which is intended to observe at least the half of the sky at the end of the mission. That's it. Thank you very much.
Thank you, Juan, for an excellent talk. Are there any questions or comments?
Can you go back to slide 21, I believe, the expected results?
This one?
Yes. What are the numbers inside the blue circles?
Numbers is the expected planets, potential planets to be detected with these masses and
so it's like 11,000, 20,000 planets you're talking about? It's such big numbers?
Yeah, with this, yeah. For 15, 20 Earth masses, yeah.
And you said on a total...
It's just theoretical, it's not really...
Okay. On a total sample of 300,000 stars, that's correct?
Sorry?
The total sample was 300,000 stars.
The total what?
The total sample PLATO will be observing. The total number of stars.
3, yeah, more or less.
well, these numbers are impressively large.
I mean, one thing is the stars you observe, and another thing is the possible planets that you have around those stars. It's not the same number. But in any case, these are theoretical expectations that maybe reality is completely different in the future. We will see.
No,
There can be potential numbers of planets in these systems, but not expected numbers of detections. At least the numbers from Kepler I know fairly well, and that can't be the case here. That would mean, basically from Kepler, for example, that it would find 7,000 planets just with the upper left box, which won't be the case. So, yeah. Well, in any case, what it shows is that PLATO should find way more than Kepler. That I think.
Yeah, that's true. Maybe the numbers are very optimistic,
say,
but yeah.
Yeah.
The design of the telescope looked rather interesting. Could you give us more details about all of these small telescopes and just a few CCDs?
Well, where was it? Well, I have no any other images which are more interesting than this one, but this is roughly the design with as a 34 telescopes with around 7-8 degrees refractive telescopes with around 8 field of view of degrees field of view, and with this 4 CCDs per focal plane of 4K by 4K. More details about what? Who would like to know? Maybe fields are what? If they are what? I didn't understand. Overlap. Yeah. At the end, you will have something like 1,800 degrees field of view. No, even more than that. There is something like there is a nice plot about that. There's something like masks that of overlapping, which are is a smart way of putting this mask and of the overlapping in order to give you more stars each time you observe. That's the idea. They are put in that way that the overlap is smart, is sufficiently smart in order to take more advantage of this design than just put them randomly. Yeah. There is an image there, but I didn't put it in my presentation. But if you go to the web page of the mission, you can see that there is a smart way of putting the telescopes in order to be more efficient. Yeah, in the overlap, I mean.
Are regular CCDs,
there will be times, 32 regular CCDs in the sense that they will be observed in I think it's with 20 seconds of measurements, and there are two which will be faster than that. 2 faster, and the other will be regular. And the 2 faster, if I remember well, they will have some color, because this is another difference with the other missions, the CoRoT and Kepler, which works with light, white light. This mission will have at least some colors. Well, CoRoT, in fact, also have some colors, but it seems they doesn't work. They don't work very well. But this mission is intended to have some colors, yeah, in order to distinguish transits or let's say activity and so on.
I'm just curious about one of the plots that you show at the beginning. You show the theoretical distribution of masses expected for the different planets. And there were like preferred masses, so rather than having a continuous distribution, did one. You see that there is a peak at 10 Earth masses, and then, I don't know, 300 Earth masses.
I think, well, this distribution is normalized by what is expected to be found in the habitable zone. Yeah, I didn't say this detail. Yeah, but apparently doing that is expected to find more stars in this for smaller planets around there.
So this is not the distribution of the masses to be expected, but something that is somehow combined with something else, which gives rise to these peaks. It's not that that nature produces planets with particular masses.
I don't know exactly the details of how they have constructed this curve, but I suppose they have used what is known today, and they have made some extrapolation, or more or less what we do in with the stellar populations or something like that. I don't know the details about this this work exactly, but it's more like predictions. Not only this work, but other works. Apparently, predictions say that there should be more planets in this smaller planets there. In any case, if they are, the only way to know is with missions like PLATO. We will see. The idea is to check if this is right or not.
We have time for one. I think we have time for one more question. Anybody?
Can you say a bit more on the planning of the mission in terms of how observations will be taken? You said in the last slide 42% of the sky coverage, and there were two large red areas. Do I get it right that these are the ones that will be observed for a long time, and then they will make short pointings on a large fraction of the sky?
Well, this is now under discussion. It is not decided yet, but there is a possibility of observe. There are two modes of discuss now. My print is coming.
We've seen it,
Too fast. Okay.
We know what we were talking about, this last slide. For a quarter second.
Oh, well, I will give you details. Well, in fact, there are two modes. One mode is observe two fields during 3 years, fix. 2 fields during 3 years, that's it. And changing each 3 months by 90 degrees the field of view, just like this, more or less.
The same field, right? Like Kepler's rotating every 3 months by 90 degrees, but looking at the same area.
I'm not sure, but Kepler, I think, is less than 90 degrees. Maybe Rafa, who is here,
No, they rotate every 3 months by 90 degrees.
By 90 degrees, okay.
I know that
yeah,
for sure.
It's more or less so. Yeah, and the other possibility is instead of 3 years is less than that, and giving you the possibility of changing the field of view and make shorter observations like 5 months for different targets. It depends on from now to in the preparation, from now to some years in advance, to see if there is more interesting one and another, depending on what we need in astroseismology to be able to give more detail or more accuracy for certain targets. Can we thank Juan?